Okay, well, I've got my fan wear on. Today is part of Spirit Week, and I guess this is Fan Day. So I'm a fan of Jesus and a fan of St. Joe Christian School for sure. I could use a fan. Come think of it, I think I'll turn on my ceiling fan. It's getting a little warm today. So I thought I ought to go over the physics practice test if you're watching. That's what this is called. Let's do that real quickly. Together, cell phone in a vacuum demonstrates, that demonstration shows us what? Sound is a mechanical wave. By mechanical, it has to have forces exerted on masses. In this case, it would be force exerted on air molecules. So sound is a mechanical wave. And mechanical waves require a medium. They have to have something to move through. Number two, classify sound waves by their particle movement relative to the propagation direction. Well, if they're moving that way, then there's two. Longitudinal, the particles move parallel to the propagation. Sound waves. They're called longitudinal because they move the same direction that it's propagating. Particles move parallel to the direction of propagation. We'll just say parallel to propagation. Same direction. Number three, describe the relative phase and interference of these waves. Well, if this wave is cresting and dropping, but the wave below it is doing the opposite, they call that destructive interference or out of phase. They don't really destroy each other, so it's kind of not a good word to use. But destructive interference, they don't interfere with each other either. That's the weird thing about waves. They're exerting forces on particles and stuff. Two waves can go right past each other in the same medium and never stop each other or interfere. But if they meet in the same point at the same time, one may be trying to push up on the particle, the other is trying to push down on the particles, in which case that would be out of phase. In that sense, the net displacement would be zero. But they're not really destroying each other. Number four, when a wave gets to the end of a string that is fastened tightly, most of the energy is reflected as an inverted wave. Because it's harder to move that new medium. They exert equal and opposite forces, but the thing that moves the easiest will move the most. Most of the energy is reflected, inverted, upside down. Crests become troughs. Sorry, you can't read that. And troughs become crests. Compressions become rarefactions, and rarefactions become compressions. Number five, acoustical impedance transformer. It focuses sound energy, not exactly. A tube could do that, but it gradually changes impedance to maximize transmission. Gradually changes the impedance. Maximize transmission. There's other ways you could word that, but the idea is like a cheerleader's megaphone. I guess it doesn't have to be a cheerleader's megaphone. It could be anybody's megaphone. But the fact that it's gradually changing the restriction of the air But you see these in other places, on a speaker. You see them on the end of a band instrument, things like that. You can maximize the transmission of sound with this gradual change in impedance. Even the outer ear is an acoustical impedance transformer, gradually changing impedance. They don't put an acoustical impedance transformer on instruments that they don't need to be louder, like flutes. Sorry, Callie. Well, anyway, no flute players in this period, I guess. They put one on the end of a saxophone because we want to hear them more, right? For sure, Tori. Okay, 6. An example of an acoustical impedance transformer is, well, the outer ear, the flared end of a wind instrument, a megaphone. Yeah, all of these, right? Outer ear, megaphone, band instruments. Increase the transmission. It doesn't amplify it by adding energy, it just transmits more energy. Number 7, if two waves travel different path lengths, what fraction of a wavelength would they have to be different to experience destructive interference? Well, if two waves are coming from two different sources like stereo speakers or something, or even band instruments or vocals or something, if they're just a little bit farther away from each other, the listener may catch some waves out of phase with each other if they're a half wavelength difference. Because halfway through the wavelength would be a compression instead of a rarefaction. Or if it was another kind of wave like on a string, it would be crests instead of troughs. Yeah. Half wavelength. Helmholtz, number 8. Explained sounds had different tone qualities because they have different harmonic content. Yeah, every sound is actually vibrating in more than one mode, not just a fundamental, but multiples of that frequency are also being vibrated. We call them harmonics. Or sometimes people call it the wave form. Exactly how is the source of sound beating the air? If it's pushing it together and it stays in that position and compression for a little bit of time, it may come off grafted like this. Sound pressure may look like a square wave, or it may be a sawtooth wave, or it may be a sine wave, nice and smooth. Those forms is what determines the quality of the sound that we hear. All right, number 9. On your practice test, it says, if C is 262 hertz, what frequency is 1 octave lower? Well, we divide it by 2. That's why octaves sound alike, is because they are beating in sync, but there's an extra beat, an extra pulse or an extra pressure front in between each of the pressure waves. We call that an octave above. So 262 divided by 2, 131. That would be an octave lower. Number 10. Two notes are played. If the frequencies of those notes are 262 and 327.5 hertz, what frequency would complete the major chord? You get 65.5. Well, it turns out that these are multiples of that fundamental. If you multiply 65.5 times 4, you get 262. If you multiply 65.5 times 5, you get the next note in the major chord, 327.5. And if you multiply it times 6, you get the next note in the major chord. 65.5 times 6. 393. Well, this times 4 is 262. That's a C. We know this is an E then in the major chord, and this is a G. C, E, and G for you musicians. They call that a major chord. Number 10. Two notes. Oops, sorry, that is number 10. Number 11. In tuning a guitar, one string is fretted on the 5th fret, and the next string is open. If both are plucked at the same time, the first string is for 40 hertz, and the second one is a lower frequency, a slightly flat. 2 beats are heard, 2 pulses, 2 fluctuations in amplitude. Any musicians that's tuned before have heard these fluctuations in amplitude. They are exactly how different the 2 frequencies are. If one is flat from 440, then it would be 440 minus 2 beats, 438. And that's why higher frequency instruments are a little harder to tune, because they could be off by 1 hertz, and that's really close to the same note, but you would hear one of those pulses, those amplitude fluctuations every second. Number 12, increasing linear density of a string. Will it lower the frequency? Sure. You see it on a piano or on the low strings of a guitar or violin. You see it on the band instruments, the ones that have the most air in them, like tubas. They have a lower frequency because they have more mass to move. They have less acceleration. F equals ma rules. But they'll also slow the velocity of the wave. So the 2 answers there are decrease the frequency and lower the velocity. Um, 13. Where are we? Turn the page on your practice test. Nikola Tesla had a small oscillating electrical generator attached to a support in a building which he lived as part of his research in AC wave transmission. He was quite the genius in alternating current. He claimed that if his generator vibrated at just the right frequency, he could transfer the energy to the building. And if it was exactly the resonant frequency of the building, it could actually impart enough energy to knock that pillar down and destroy things. Legend has it that it did occur. The police were even called to the area, and they investigated, and he smashed the little vibrator just in time before the building started showing signs of crumbling. What is this frequency matching phenomena called? Resonance. One of my favorite phenomena. From a child on a swing to microwave cooking, all of it is about energy transferring because of frequency matching. And it certainly happens in music. Number 14, human ear concentrates the sound energy for maximum movement of particles in 4 different ways, really. The outer ear is an acoustical impedance transformer. Big word. Transforming the acoustical impedance gradually. And as you move into the next part of the ear canal, Well, see, the eardrum. Well, let's go with the ear canal. Ear canal is a closed tube. It has a resonant frequency. That actually helps you hear certain frequencies more than others. Then the eardrum, of course, the eardrum is larger than the oval window. The tympanic membrane. By doing that, it creates a hydraulic effect. So that you could think of it as all the energy that the eardrum captures is concentrated onto a smaller window, which is what opens up into the cochlea and has the fluid in it. The bones of the middle ear, they actually pivot on each other like a lever. Bones have a mechanical advantage, you could say. It's actually a ratio of about 2 to 3, and that means that it has more movement output than what the input is. It's amazing how God has designed the human ear to hear things so well. We can hear tiny, tiny amounts of energy. A millionth of a watt per square meter. Okay, 15. What we perceive as pitch is measured as frequency. These are just qualitative terms, pitch, quantitative term, frequency. 16. The period of a simple gravity pendulum is determined, except for the acceleration due to gravity. They actually can measure acceleration due to gravity with pendulums and to locate oil fields and natural gas fields and things, because little g is different in different places depending on the rock formations below. But other than that, pendulums are determined, their period, by the length of the pendulum. That is the only factor. The mass on the end of the pendulum does not affect it. The angle, as long as it's not too big of an angle, also does not affect it. Something that Galileo noticed as he watched the cathedral lamp swaying and used his pulse, perhaps, or he sang a song to keep time, and he noticed that as the oscillations died down, the period of time remained constant. Somebody used that idea to make clocks. Where are we? Number 17. Which of the lettered lines? Well, they're not lettered, but you know, wavelength would be from a crest, to one point on a wave to a corresponding point on the next wave. That would be wavelength. Don't worry about the letter. Number 18. Which lettered line shows amplitude? Well, if the dotted line represents the rest position of the wave, then amplitude would be the displacement from that rest to the maximum displacement. So that would be amplitude right there. And number 19. An exhaust pipe is an open tube 3 meters long. What's the longest wavelength that it will produce? 3 meters long? Well, it would produce a wave twice that long. Because if it's an open tube, if you remember, the open tubes would produce a antinode at both ends, and antinode to a node is a fourth of a wavelength, to the next antinode is a half a wavelength. Node to node or antinode to antinode is half wavelengths. There are other waves that can resonate inside of that open tube. Band instruments, of course, are open tubes, and they have different notes they can play. Okay, if the exhaust gases are 30 degrees, how fast does sound travel in the pipe? Well, we want to add a little bit. Uh, if it's 30 degrees, when it's 25 degrees, it's 346 meters per second. We need to add a little bit because it's warmer. How much do we add? We add 0.6 meters per second for every degree above 25, which would be 5 degrees. So we add that. Take it times 5 degrees per meter per second. And so we want to add 3, right? So it'd be 349 meters per second. 5 times 0.6. Number 21. If the sound traveling 330, frequency is 3,300 hertz, the wavelength is? Well, the simple equation, the relationship between wavelength and frequency is that lambda f is v, velocity. We want to solve for lambda. V divided by f is wavelength then. So the velocity 330 divided by 3,300 meters, or sorry, per seconds. If you want to see the unit labels cancel, you could also write that as hertz. It's the same. And the wavelength we see is, dividing 0.1 meters. The unit reciprocal seconds then cancels. 22. Well, let's get a new board here. 22. Whoop. Can you write? 22. 40 decibels, if you remember. That would be 4 bells. And that is the log of the increase in frequency. The power on the 10. The power on the 10 would be a 4 then. That's 10 to the 4th. So that's how much louder it is. 10 to the 4th times. Ten to the 4th times. "23. Consider the closed tube, the human ear canal. Um, 3.2 centimeters long. How long is the wavelength of the fundamental standing wave or the first harmonic? There we go. 23. Of course, the wavelength, because a closed tube, if you remember, has a node at the closed end and an antinode at the open end. That's only 1/4 of a wave. So the wavelength is going to be 4 times that long, which is 4 times 0.032 meters, if you want meters. You can leave it in centimeters if you want to. But 0.128 meters would be the length of the wave that resonates in the ear canal. You could calculate the frequency then. 24. If the speed of sound is 37 degrees, is 353 meters per second. Where are we? 350 meters per second, 32 degrees. The wavelength of the first harmonic. What frequency would resonate best in the ear then? Yeah. Again, we use V as lambda f. The frequency would be V divided by lambda, the wavelength. So we could take the 350, the speed of sound in the ear canal, divided by the 0.128 meters. And that's the frequency we would hear. 350 divided by 0.128. 2,700 meters, or sorry, per seconds, or hertz. to two significant figures, 2,700 per seconds. If you don't like that per second expression, you could write s to the negative 1 power. Or you could write 2,700 hertz. All right, number 24. And number 25. So, what effect does increasing the amplitude of a simple harmonic oscillator do to the frequency? 25. That's the beauty of music. That you can increase the amplitude, but it doesn't change the frequency. You can play a note louder, but it's still the same note. No effect. Essentially, that is God's gift to us because of Newton's second law and Hooke's law of elastic systems. Then we see that larger amplitudes, we derived this in class, larger amplitudes have no effect on the frequency. Thank you, God, because I love music. And it would be impossible without that simple law relationship. Those two laws right there. F equals ma and F equals minus kx. Simple little math. And voila, we have music. As well as the simple multiple relationships between octaves and major chords, major fifths and major thirds and so forth. Harmonics are another wonderful mathematical expression of God's love for us. Number 27, hydrogen and helium have much less mass per volume. You put that in your nose, everybody's probably heard people breathing helium from a birthday balloon, and then your voice sounds funny. It isn't because it's higher pitched. The gas doesn't come out faster significantly. Instead, it has nothing to do with the tightness of your vocal cords, but instead, it's because, the multiple choice, the lower density gases resonate higher frequencies that are in your voice. Yeah, is this 26? Did I skip one? Oh, sorry. 26. Sound waves that a trombone can produce constant length have something in common with electron waves around a nucleus. In both examples, the waves are quantized. That just means that only certain notes can be played in a particular horn length. They jump, quantized. Electron waves are also jump in energy. There's no in-betweens. It's stepwise as opposed to continuous ramp-wise. Now, if you slide your slide, you're gradually changing the length, and you'll get all the different notes in between. But in one position, it's always quantized. Now it would be like 27. The hydrogen-helium gas has less density. That means the higher harmonics in your voice, because your voice is really a mixture of several different frequencies, all multiples of each other, the higher harmonics are enhanced, or they resonate better with the lower density gas. All right. Yeah, 'tis a mystery. And if you do that and listen closely, as the lower density gas escapes and the regular air, normal density gas takes its place, you'll hear your voice returning to normal, but all the frequencies are actually still there. You just hear the lower ones a little louder when the air is in your lungs. You hear the higher parts of your voice when there's helium in your lungs and your nasal cavities and so forth. 28. What law, demonstrated by the fact that Greater tension in a string, which makes frequency higher, and more mass per unit length lowers the frequency. What famous law? Yeah, we just mentioned it a minute ago. F equals ma. It explains almost everything. Of course, it's not perfect. It doesn't explain everything. We have no complete, perfect law or theory about any scientific phenomena. Science is just models, equations that we use to help us predict things and explain things and enjoy God's creation for us. He is a God of math, a God of love. Number 29, a note on a standing wave. It's a place where waves pass each other out of phase. Or meet each other. In this case, they're actually going opposites, so they pass each other out of phase. There's the net force acting on the point, whether it's air or whether it's a string, is 0. Net displacement, 0. Number 30, wave changes direction because it's change in speed. It's called refraction. We see light doing it all the time. We don't think of sound doing it, but it actually does. If you've ever over a lake, you may notice sounds at night a lot further away than during the day, because at night the air further down is cool, the warm air rises, sounds coming from one side of the lake are actually sped up in the warm air and they swing around and they come back down. So sounds that normally would escape are actually coming down. Now, if there's lots of water, it may reflect off of water, refract off of more sound, more warm air, and reflect and refract several times. It's kind of a little tunnel that it'll direct sound for a long distance. We hear sounds better at night because of this temperature inversion. The process is called refraction. You also see it with light, warm air on right above a highway or blacktop. The same thing occurs. Light, though, is being refracted by it's of course the opposite direction. Maybe there's a tree in the distance, and light from that is sped up in the warm air close to the road, and the waves tend to swing around and come back up. It almost looks like water, but it's actually refraction off of warm air. I wish we had more time to talk about that. It's fun stuff. Number 31, when a wave spreads out, circular wave fronts going through an opening, and maybe you've seen this with water, but wave fronts meet a barrier, and like a doorway, this can actually happen with sound. As it goes through, it spreads out. It's called diffraction. Yeah, you can hear around corners. You can, even light will do that. Water waves certainly spread out through an opening. Number 32, vibrating force matches. We call it resonance. Frequency matching. This is a brief definition for resonance. We've talked about it already. Amplitude of a sound is perceived as loudness. And we call it amplitude when we're talking about it quantitatively. Loudness is a qualitative term, but it's squishing the air together more if it's louder. Higher pressures, When a source of waves is moving toward you, the frequency observed is higher. We call that the Doppler effect, because the waves are all kind of pushed together and closer together. It's called the Doppler effect. Higher. Number 35. The velocity of a wave is determined by temperature, density, and elasticity. Faster particles move sound faster. Higher density things like steel, even water, moves sound faster. And if it's more elastic, like steel, it moves the sound much faster. Number 36. How many decibels is twice as loud? Well, 10 to the 0.3 power is 2. So it's 0.3 bells, or 3 decibels. We perceive changes in loudness logarithmically. That's an interesting phenomenon too. God's just a mathematician all the time. And we're at 37. What does yours say? The velocity, let's see, a harmonic. Oh, a harmonic is a whole number multiple. Whole number multiple of the fundamental frequency. Fundamental meaning the lowest frequency that a medium will produce, an elastic system will produce. Multiple of fundamental frequency. "38. Still awake? Amazing. We're almost done. Wave encounters a high impedance medium like a string tied to the faucet. We saw what happens. The reflected wave is inverted. What will have to form? Well, if it's an inversion, the wave that's coming will have to be out of phase with the wave that's leaving. It'll always form a node. And you'll notice that at the end of every wave exhibited by a string, it will be a node at the two ends. That's the only rule. You can have no nodes in between those two nodes, or you can have multiple nodes. If you get that string vibrating, it's going to be a node at both ends. But you could also have a node at both ends and a node in the middle as well. Kind of vibrating like that. Or two nodes in the middle, or whatever. So 39. What did I get off? If you thought outdoor worship was too loud and decided to move 10 times further away, how much less? The outside, that way you don't get reflections off the walls, and the sound spreads out. The sound spreads out isotropically in all directions equally. Well, you would get the inverse square of that, 10 times further away, inverse square, you would get 1/100th as much sound. So yeah, getting further away from a sound source diminishes the sound intensity significantly. Oh, what's 100 times quieter? That would be 20 decibels less, right? Because it's 10 to the 2 power, 20 decibels less. Number 40, how would tightening a string affect its velocity and wavelength? It would be faster and longer. Faster velocity. We were going to do a lab on how strings vibrate and make different standing waves and do some measurements with linear density. Sorry we didn't get to do that, but we'll do other fun things. faster velocity and longer wavelength. Because it's moving faster, it's going to move further down the string, longer wavelength, lambda. All right, 3 equations again. God has created the world in a way that we can express with mathematics. And again, He is a God of order, not a God of disorder. He is not a God of confusion. We find a certain peace in knowing that things are orderly. Our worship is supposed to be orderly. We learned that in Bible study. Thank you, Mr. McDonald. So we put those 3 equations together to solve for frequency. Turns out the frequency is the velocity divided by the wavelength, 2L. I'll just write it out in one line. We'll multiply this expression times the 1 over 2L. T stands for the tension in the string. Mu stands for the linear density. How much mass does it have for its particular length? Well, we plug in all of the terms. In this one, the length is 0.5 meters. 2 times 0.5. We take the square root of the tension, which is given as 0.288 newtons. 288. Have you heard the joke about 288? I've told you before. It's too gross. It's too gross. Get it? I had to have one pun. All right. 288 is too gross because 188 is 1 gross. If you need to explain that to your parents. I know you've heard it before. Mu, the linear density, is given 8.42 times 10 to the minus 4th. Kilograms of mass per unit length meter. Ooh. Let's plug all that in and see what we get. I got 18 hertz. Check me on that. But it's 0.288 divided by 0.288. Whoa, clear that. 0.288 divided by 8.42. Enter exponent negative 4 equals, oh, that's not what I got last time. Square root of that equals, okay, try it one more time. 0.288 divided by 8.42, enter exponent negative 4 equals 342. Square root of that, 18, divided by 2 times 0.5, which is 1. Yeah, 18 to 2 significant figures. All right, let's try number 42. Motorist is traveling 42 meters per second. Is on a nice day, 25 degrees. The speed of sound is 346. He sounds his horn 512 hertz to alert a stationary pedestrian of the danger of 2 tons of speeding metal coming toward him. What frequency would the pedestrian hear? So we are talking about the Doppler effect. The frequency heard will be the frequency of the source times 342, the speed of sound, 346, sorry, the speed of sound plus or minus the speed of the listener, L, divided by the quantity speed of sound minus or plus the speed of the source. Well, this is going to be 0. This is 512 from yours. The quantity speed of sound 346. That's a quantity of 0 plus minus 0. divided by speed of sound again, but this time, it's supposed to be meters per second. Meters per second. Do we add or subtract the source of the speed of the source, which is 42 meters per second? 42 meters per second. Well, remember doing this with the assignment. We know that if it's coming toward, it has to be a higher frequency. Agreed? Higher frequency. So we want the numerator to be bigger than the denominator. So the number will be bigger than 1 that we multiply times 512. So we want to subtract the 42 from 346. Oh, well, I got 583 hertz to 3 significant figures, which I think we can keep because you're given 3 in all of the numbers. 346 divided by 304 is a factor of about 1.1 something. Multiply times 512, 583. I've said it before, I'll say it again. These mathematical expressions and our ability to examine the world, certainly our ability to enjoy music, and we know that you can't explain that with just math. But the fact that we enjoy music says that there has to be a God, and He loves us.